Alright, hello class. So in this video we're going to be sort of leaving the realm of all the advanced integration techniques. Partial fractions was thankfully the last one we're going to look at in this particular class. And move on to start looking at applications of integration and the linking topic that we use to do that, or at least I like to use to do that, is a subject called improper integrals, and which I always find a kind of amusing name because some would argue that all integrals are improper. But what improper integrals deal with are when you have infinities showing up in various places. Okay, so I think the easiest way to start looking at this is through an example. This kind of goes in the opposite order than the book does, but I think this order I'm about to show is actually more natural. It's more naturally occurring. Okay, so let's just jump to an example real quick. Okay, just to give us a quick reminder, we haven't gone through a lot of examples of definite integrals in this class so far. That's because when I'm talking about integration techniques, I kind of want to just focus on finding the antiderivative versus worrying about plugging and chugging and things like that, because that part basically always works the same. Once you have the antiderivative, you just plug this stuff in and go from there. But one thing that some people maybe aren't that careful about when it comes to fundamental theorem of calculus, which I always abbreviate to FTC, it's this wonderful little thing here, that the definite integral from a to b of a little f of x dx is equal to capital F of b minus capital F of a, and this is where capital F of x is an antiderivative of little f of x, and f of x is continuous on the interval a to b. Okay, and this is something that I think a lot of people maybe don't think that much about, this part here, that f needs to be nice and continuous, and shouldn't have major jumps. The thing is, though, that if we're looking at a function that maybe just has a hole somewhere, right? Maybe it has a hole right there, but just a single hole, okay? If I were to find the area beneath that curve, well, the area is not going to change just because there's a hole there. Right, so for some cases, this continuity restriction maybe isn't fully necessary, because what we could do, if there's just a hole, well, we fill that hole back in, and you just maybe pretend like it's not there. So for what we would call a removable discontinuity, it's not really going to affect the area beneath the curve, which is our definite integral. Okay. However, if we have some other type of discontinuity, we can run into some weird issues. So let's take a look at an example where you might cruise through with the fundamental theorem of calculus without being very careful about the function you're looking at and get something that doesn't really make much sense. Alright, so let's say we have this integral here. We want to find the definite integral from -1 to 1 of 1 over x squared dx. And suppose you just go through it like you normally would. You don't really think about what your integrand is. You just sort of say, okay, this will be the integral from -1 to 1. That'll be x to the -2 dx. All right, nothing super weird there. Now I'll do the power rule. So that's when we integrate will be -x to the -1. And we'll do our fundamental theorem of calculus step here. So, which is we'll plug in the 1. So we'll get -1 to the -1 minus a negative. All right, so we can already see that this is getting hairy. Let me make this a little easier on myself. Let's rewrite this as this is -1 over x, evaluated from -1 to 1. All right, so I'm not dealing with a bunch of powers. All right, so I'll plug in the 1, so I have -1 minus a -1 over -1. So that will be a +1 here. So the whole thing comes out to be -1 minus 1, so we get -2. Okay, and so you move on with your life, and you say that's the answer, and, well, the problem is you're completely wrong. Because remember, the definite integral gives you the area between the curve of f of x and the x-axis. All right, now negative, this means that, right, a negative definite integral means the function, I'll just call it f of x here, lives below the x-axis for most of its life. And that's our first issue. If we take a look, let me try and get a good axis going here. Hang on. Okay, so this graph, this 1 over x squared, here's where we run into our first problem. This is always positive. It's always above the x-axis, but we got a negative integral. Okay, which means it should live below the axis for at least most of its life from -1 to 1, but it doesn't. In fact, 1 over x squared is always positive, so we should always get a positive integral here. And not only that, at -1 we'll get 1, at +1 we'll get 1. So if we look at this rectangle here, okay, the area of this rectangle is +2. Okay, so we have a base of 2, a height of 1. So even if we just made a little mistake with our sign here and said, oh, okay, well, it can't be -2, it's just 2, the problem is we still have all this area up here that we haven't counted. Okay, so the problem is that 1 over x squared has a major discontinuity at 0, right? So 1 over x squared blows up at 0. So this isn't even a case where we could, oh, put the missing point back in, it's not going to affect the area at all. We've got this like crazy blow up thing here. So the question that naturally arises is, well, are we stuck? Right? Are we stuck? What is this area in the pink here? Okay, can we actually calculate this? Now, before you ever had calculus, you might have thought the answer was no, because, oh, it goes up on and on forever, so, you know, it can't. It's got to just be an infinite area. Okay, but after at least calculus 1, I hope you are at least a little more skeptical about thinking of that immediately, because when infinities start getting involved, we could actually end up with anything. Okay? So here's how we tackle problems of this type. Okay? So I'm going to simplify it a little bit because I only really want to look at one side. All right. So I just want to look at the integral from 0 to 1 now. Right? Just to simplify, I don't want to break this up into two pieces. So how we would progress now is we're not just completely done. What we're going to do is just proceed like we normally would. Right? Say that that's x to the negative 2. And then integrate like normal. So we'll get negative x to the negative 1. And that is going to be negative 1 over x from 0 to 1. This is our fundamental theorem of calculus thing. Now, here's where we run into the problem, is we can't plug 0 directly into here because we get division by 0. Okay? However, when we do, if we were to just do that, so if we plugged in the 1, then minus the negative 1 over 0, well, that's of course undefined. But if you remember from Calculus 1, the constant over 0 case means that we have a plus or minus infinity. All right? Now, that's what we would expect from this problem, right? Because this function jumps up, we have a vertical asymptote, we have blow up, and it never dies down. So we get what some would argue must be infinite area, right? Because it just goes right off the screen. And I could keep this going forever and ever and ever if I wanted to. And eventually it would just start looking like a line. All right, and just imagine it continues on forever and ever and ever and never stops. So it makes sense that, in some cases that's going to be infinity. So this is a plus or minus infinity case. So what people do, since we can't just plug that in, what they do is they say, okay, let's change this. Let's say it's the limit as a goes to 0. Okay, and we're approaching 0 from the right, so it's literally just 0 from the right, okay, of negative 1 over x evaluated from a to 1. So now we can do our fundamental theorem of calculus step with a limit sitting on the outside. Okay, so we'll get negative 1 over 1 minus a negative 1 over a. And we'll get negative 1 plus, and of course I forgot my limit signs. So a going to 0 from the right. We'll get negative 1 plus 1 over a. Now, a constant over 0 is a plus or minus infinity, so you always have to just figure out which one it's going to be. Since we have 0 from the right, this is not, what I'm about to write here, this is not considered standard proper notation, but I like it because it helps me sort of figure out what's going on, because here I have 1 over what I call a positive 0, so that's going to be a positive infinity. And then subtracting 1 is not going to affect that, so we go to a positive infinity. Okay? So, what we say, so here, we say that this integral 0 to 1 of 1 over x squared dx goes to positive infinity. In other words, what we like to say in this case is the integral diverges. All right, now that is going to be important eventually. Okay. If it actually went to a number, we'd say it converges. Okay. So some of the problems from the book will ask you whether the improper integral converges or diverges. That's what it's saying. If it goes to plus or minus infinity, or just the limit doesn't exist, it diverges. So if the final limit goes to plus or minus infinity or just doesn't exist, that implies divergence. Okay. All right, so does this always happen though? I mean, that's a pretty natural question. Would this always happen? So let's just take a look at another example and see what we get. Okay, so let's take a look at this. Let's say we're looking at the definite integral from 0 to 1 of 1 over the square root of x dx this time. And we have a similar thing going on. 1 over the square root of x blows up at 0. And I've kind of exaggerated my graph here. The difference is as x increases out this way to the right, it does decrease down to 0, but it does it slower than 1 over x squared does. And it still increases up to 0, but it gets closer to the y-axis faster. Okay, so let's start integrating this, and what we're going to find is that this one may not have ever given you trouble if you looked at it before, because this would be x to the negative 1/2. Right, so when we integrate that, that's going to be x to the 1/2 over 1/2. And that will be 2 x to the 1/2 from 0 to 1. And we get 2 times 1 to the 1/2 minus 2 times 0 to the 1/2. This is our fundamental theorem of calculus step. And we just get 2. Okay, well, this function had blow up, right? This is definitely blowing up. But what ends up happening is much faster eventually. Okay? This ends up being really, really close to just being a line. And a line has 0 area. Okay, so some functions get so close to the y-axis so fast that eventually all you're doing is adding up a bunch of zeros up here. Okay, so it eventually goes to this area here goes to 0 fast enough to cause the integral to converge. So we didn't even notice that there was a problem here. It turns out there was. In fact, what we probably should have done is put in a limit, but since we can just plug in the 0 here and get no problems, the area ends up being 2. So what ends up happening is probably here is this area is probably really, 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 really close to 2. Right? Maybe like 1.99999, something like that. And then what we're adding here for the rest of it is the 0.00000 whatever. Okay. And it's all about how fast does this function get close to the y-axis, or whatever line you're looking at, right? So that makes this happen. How fast is it getting there? And Is it getting there fast enough to eventually just zero out while we can still see it? So our last function, apparently 1 over x squared, doesn't do that. It doesn't get close enough to the y-axis fast enough. I mean, it still does, but it doesn't do it fast enough in order to get a finite area out. Okay, so actually, I've prepared some graphs with some actual software so you can better see what's going on here. Let me pull those up. All right, so here in blue on this graph, this is the 1 over x squared. Okay, and you can see that even if we zoom out, it takes a long time, relatively speaking. Okay, we just keep zooming out, and we see we still have space in between the y-axis and the graph, right? So it takes, I mean, even on my screen, I can still see some space, and we're all the way up here at 70. Okay, so 1 over x squared sorry if you have sensitive stomachs or something. So 1 over x squared, yes, it does blow up, and just like the 1 over the square root of x and 1 over any of the positive powers of x. But if you compare it to 1 over the square root of x, which is here in orange, you see almost immediately it's right on the y-axis here. At 10, even here at 8, I can't tell a difference between the y-axis and the graph itself. So it shrinks down real fast, okay? And we can see the difference between it and the other function, 1 over x squared. We can see the difference between the two pretty dramatically as we zoom out and look up. I mean, it just looks like our axis is orange. Okay, so these are things that are large enough. Yes, they might be small areas, but they're still large enough that as we continue to add them up over and over and over again, okay, we still, so let's zoom in really close. Okay, here I'm zooming in. And you can see when we zoom in up here at like the 150 mark, close to it, we still have so much room between the 1 over x squared and the axis, while the 1 over square root of x is right on the axis. Okay, so yeah, these areas are going to be really close to 0 because this is 0.1 right here, this line. Okay. However, it's not close enough. Like, we still have a lot of area that we are adding up as we go, but on the other hand, the orange thing is just a line. In fact, I can zoom in as close as I want, and eventually it takes us, well, this line right here is 0.0001 right here. Okay, so we have to get within a domain of 0.0001 before we can even see the orange line off the axis. So that's what's going on here, essentially, is we are looking at two different functions. One goes to 0 so fast that it might as well not be infinite, while the other one, it doesn't go to, the areas don't go to 0 fast enough to finally level out and actually give us something meaningful. Okay, so those are the two possibilities that we have. Okay, so finally getting back to what we were talking about, what we would say is that this definite integral here converges to 2. So the definite integral 0 to 1 of 1 over the square root of x dx converges to 2. All right, so let's look at another example of this type, and then we will look at the other type where we go out with infinite limits. All right, so let's take a look at the integral from 0 to pi over 2 of tangent of x dx. So tangent of x, well, remember that's sine over cosine. Okay, so at 0, we'll get 0 over 1, so that's no problem, but it's the pi over 2. At pi over 2, so let's take the limit here. This goes to a 1 over 0. Okay, so that's where we have the blow up. And in fact, if you look at a graph of tangent, if you've ever graphed tangent, you know that it basically blows up, and over on this side it kind of does the same thing, but it just does it over and over and over again. Okay, so it has a repeating blow up if you look at the graph. All right, so what we're going to do is just start integrating like normally, and then when we have to start plugging things in, we'll start taking a look at what's going on with a limit. All right, so the integral of tangent, as we've talked about, we could either do u substitution, or we could just remember that it's going to be the natural log of the absolute value of secant of x. Okay, now secant of x, remember, is 1 over cosine. So secant is 1 over cosine. It's going to have the same problems right here. So when we plug pi over 2 into secant, that's going to give us a 0 down here. Okay, so what we can do is introduce a limit, okay, or we can just say, all right, we're approaching pi over 2 from the negative side. Okay, so officially what you need to do is just write the limit as like a goes to pi over 2 from the negative side of the natural log of secant absolute value from 0 to pi over 2. All right. So what we'll do is this will be the limit as a goes to pi over 2 from the negative side. And you know what I often do is just this. I'll show you. It's unofficial, right? Don't show this to some of your math professors because they might get grumpy about it. But I'll just plug it in and say, okay, this is going to be the natural log of the absolute value secant at pi over 2 from the negative side. Okay, and then minus the natural log, the absolute value of secant of 0. Well, secant of 0 shouldn't be a problem. Okay, so here's what we need to establish, right? Secant of pi over 2 from the negative side is going to be 1 over cosine of pi over 2 from the negative side. Now cosine, all right, it looks like this. It starts up positive and then whoop, it hits 0 here at pi over 2. So from the negative side, cosine should be positive. Okay, so cosine, let me give myself a little more room here. This cosine should become a 1 over 0 positive, right? It goes to a positive 0, right? I don't know, that's just kind of the way I think about it. So what we basically have is the natural log absolute value of 1 over 0 positive minus the natural log the absolute value, and I guess it doesn't really matter whether it's a positive 0 or negative 0 here because we're taking the absolute value. I just thought about that. And then secant of 0 should just be 1, and then the natural log of 1 is 0. So really, we're just down to what we have here. Okay, well, this is a plus infinity. Now, this is bad form right here. We're not usually allowed to just plug in an infinity, okay? But I do. Just to, because, you know, if I needed to write this as a formal math paper or formal homework, then I would put my limits in. But anyway, natural log looks like this. So as x goes to infinity, natural log goes to infinity. So this goes to a positive infinity. Okay, so it turns out that this integral diverges. Okay, now the next type of improper integral is just, well, if we could do it one way where the function blows up vertically, we can also do it for the horizontal asymptotes where the function levels off over time, right? So if we go back to our graphs, okay, of our it's the same graphs we were looking at before. The 1 over x squared is here in the blue. And you see, though it didn't blow up, it didn't get close enough to the y-axis over here when we were looking at it from 0 to 1. If we looked at it from 1 to infinity, it jumps down to 0, the x-axis, really fast, while in orange, the 1 over square root of x, it has the opposite behavior as we let x increase. Okay? So it turns out we get, it usually turns out with these 1 over x to some power that we get opposite behavior, whether we're looking at the vertical asymptote or the horizontal asymptote. Okay, so it's the same idea. We're trying to see, does the function get to 0 fast enough, right? So does f of x shrink to 0 fast enough to get an area out? Okay, like here, maybe, all right, it's hard to tell, but if I sort of redrew a new function and said, okay, it does this. Okay. It looks like if I looked at the area here that, yeah, this one looks like it just kind of past this point is negligible. Okay. So let's look at some examples and see how we go about it, but it's pretty much the same way, right? You deal with this infinity somehow. Okay, going back to the function we looked at before, the 1 over x squared, let's just look at it instead of from 0 to 1, from 1 to infinity. And it would integrate the same way, 1 to infinity of x to the negative 2 dx, right? And we would get negative x to the negative 1 from 1 to infinity, which will be negative 1 over x evaluated from 1 to infinity. Okay, now here's where a lot of mathematicians are going to get mad at me. I'm just going to plug this in, all right? Usually what you would do is you introduce a limit, right, and whatnot, but I'm just going to say, okay, this is negative 1 over infinity minus a negative 1, so plus, oh, no, not a negative 1, minus a 1. No, I was right the first time, sorry. right? Because it's minus, and we already had the minus there, so yeah, it's a plus 1. So what we end up with is a negative 1 over infinity plus 1. Well, a constant over infinity zeroes out. And I really shouldn't put equals there. I should say goes to. All right. So this guy zeroes out, and then we just get 1. Okay. So yeah, it turns out that 1 over x squared goes to 0 fast enough to converge. Okay. So this guy converges. And we'll find the opposite behavior when we look at 1 over the square root of x. Okay, let me break this off a little bit, because we'll get 1 to infinity of x to the negative 1/2 dx, which will be 2x to the 1/2. We've done this enough times now. And we'll get 1 to infinity. Now you'll notice when I start plugging in infinities, I always switch over to an arrow, because what I'm saying is that it's not equal to this, it's going to this. It's subtle, right? If you're a mathematician or a math major, it may make a difference, but for right now, I think it doesn't. Okay, so we'll get 2, and I'm plugging in infinity into the 1/2, which a lot of people, again, would fuss at me for that. And then we get minus 1. All right, well, square root, or the x to the 1/2, or the square root of x, looks like this. So it eventually goes to infinity. So 2 square root x goes to infinity as x does. Okay, so this whole thing is going to infinity. The infinity takes over here, because the minus 1 isn't going to do anything. So this guy diverges. Okay. All right, and it turns out we have this particular property that a definite integral with an infinite limit, so a to infinity, so it actually doesn't matter where we start. We've been starting at 1, but you can really start anywhere. And a just needs to be positive here. So if you have a positive starting lower limit, okay, what ends up happening is if you're taking the integral of 1 over x to the p power, this integral converges if p is strictly greater than 1. So 2, for example, we got convergence. If we put in 3, we'd get convergence. If we put in 1.2, we would get convergence. However, it diverges if p is less than or equal to 1, right? So if we do equal to 1, so if we just look at, say, the integral from 1 to infinity of just 1 over x, we're actually going to get divergence here, because we'll get, that's the natural log, the absolute value of x. Okay, and when we plug in infinity, and I'm going against my own rule there, I need to put arrow. Right, when we put in the infinity, well, that goes to infinity. So we get divergence if the power is actually equal to 1. Okay, so this is actually a really important property that we'll be using later. Okay, I'll definitely identify that when it comes up, but this will be important moving forward in a few chapters. Okay. All right, so let's look at some other examples, something that maybe isn't just a 1 over x to some power. All right, so in this example, we're actually doing quite a few things all at once here. We're taking an integral going to negative infinity, so it will work similarly, and this also will involve a u substitution, because this integral here, now I could do a quick u substitution, but I do want to show how you can approach u substitutions with infinite limits. So I'm going to want to do a u sub, and the reason I want to do a u sub is I see, oh, I have like secant squared of some stuff, then I have a version of the derivative of the stuff sitting out here. So if I let u be 1 over x, then du is going to be negative 1 over x squared dx. So really, I'm going to be replacing this with a negative du. Okay, so this will be our u. These together will be our negative du. And then our limits here are in x's. So we have x going to negative infinity here, and x going to negative 4 over pi here. So when I get to my new integral, I need these to be in terms of u's. Okay, and when we do this, it should simplify the integral a lot more, so it's nicer. So we'll have secant squared of u, and it will be a negative du. All right, I just put the negative outside. All right, now to find our new limits, if x is going to negative 4 over pi, okay, well, that means our u, which is 1 over x, goes to 1 over negative 4 over pi, which will be negative pi over 4. Okay, so that looks like a much nicer limit to deal with. Now I'm just going to put it in the same spot as this one, because we're just transforming everything in the same space. And then if x is going to negative infinity, okay, now here's where we have to be careful. U is 1 over x, so u should be going to 1 over negative infinity. So constant over infinity, that's going to be 0. Okay, so u will be going to 0. All right, so here are our new limits, 0 to negative pi over 4. Now that's a strange way to do this because it's out of order, right? But we also have this property that we can negate an integral to flip its limits. So let's do that. So it already has a negative, so I'll negate it again to get this to be negative pi over 4 to 0 of secant squared u du. All right, so now we have an integral that we can actually work with when we integrate this. And notice I'm putting arrows here because we still have this infinity. We've just rewritten how it's represented. Okay, so we'll have tangent of u, and we'll evaluate that from negative pi over 4 to 0. Okay, so it'll be tangent of 0 minus tangent of negative pi over 4. Okay, so tangent of 0 is 0. Tangent of negative pi over 4, well, tangent, we can always take the negative outside, just like we can with sine. And tangent of pi over 4 is 1. So this integral comes out to converge to 1. Let's take a look at a graph and see if that actually aligns with what we're seeing here. Okay, so here's a graph of 1 over x squared, secant squared of 1 over x, and close to 0, if we kind of pan up here, we see some very strange behavior happening. So around 0, like, we get all sorts of weirdness happening, which sort of makes sense. At 0, we get blow up here and blow up here. But we weren't looking at that. We were looking at, if we go back to our original integral, we were looking from negative infinity to negative 4 over pi. So we were actually looking like out here. Okay, and we can see that on this graph that it does shrink down to the axis real fast, like almost instantly. And that's what we saw analytically as well, using our mathematics. Okay, so I will say a graph is not always enough, because the graph can be misleading. Okay, but a graph and the analysis, and to just verify what I'm talking about, this is the analysis. Okay, with the graph and the analysis, we see that it does go to 0 fast enough. This graph does go to 0 fast enough in order to have an area, right, to have a value. All right, so I think we've got time here for another example, so let me throw another one in, just to give us a little more practice with this stuff. All right, so for this example, we're looking at e to the square root of x over square root of x. This is another situation where we have, this is of the first type, right? It's the 0 that causes the problem, because at 0, we're dividing by 0. Okay, so this would be a blow-up example. We'll look at a graph in just a second, but for this one, I'm just going to do a quick u substitution, because what I have is e to the stuff. All right, and so if I do a quick u substitution, so I'll break this up like this. Okay, and actually, I can drop that now. I'm going to do a quick u substitution, so I'll leave this x thing alone. I'll do the normal integral like I usually would, so e to the stuff, its integral is itself, and then we need to divide by the derivative of the stuff, so that's the derivative of square root of x is 1 over 2 square root x. Okay, and then we'll evaluate this from 0 to 8. Oops. Okay, and if you don't see it yet, we have some cancellation here. So I'll go ahead and invert and multiply. This will be 1 over the square root of x times, this would be 2 square root of x over 1 times e to the square root of x, which we'll evaluate from 0 to 8. And the square root of x's cancel, which is what we need for quick u substitution to work. Right? Remember, so this is the need for quick u substitution. All right, now since that all cancels out, we get 2e to the square root of x from 0 to infinity, and it looks like we're going to get, oh nope, too many infinities rolling around. That's not infinity, it's 8. Okay, sorry about that. So we get 2e to the square root of 8 minus 2e to the 0. So we can factor out the 2 and get e to the, well, what would that be? 2 root 2 minus 1 if we wanted to be super specific. So it turns out that this guy does converge. All right. Let's look at a graph and see if it jives with what we just said, or what we just found. All right, so here in blue, we have the graph of e to the square root of x over root x, and remember we were looking from 8 to 0, and it does get really close to the y-axis really fast. Okay, So it does sort of make sense that eventually all this up here, all these areas would just be 0, and what we're really looking at here is this area right there. All right, and that's actually kind of a funky looking function. If you look at the whole thing, it's kind of it's almost like a check mark. Anyway, so that should be enough to get you rolling on the homework, and just store this in the brain box for a little while, because we'll be coming back to this once we get through the other applications, and then get to the last part of what we'll be talking about in the semester. All right, cheers.